Hi, today we're going to study again stationary points, and we're going to focus particularly on the curvature of the functions, that is the concavity of the functions. And the way that we assess that is to again use the second derivative. So I'm going to show you right now how we would do it. Okay, now let's focus on the stationary points that we've mainly looked at so far. We've had a local minima or minimum points and local maxima or maximum points. So let's just label those. Okay, so we've got min and max. Now, in this particular example, in both cases, dy by dx equals 0. But also, d squared y by dx squared is, in the minimum case, is positive, and in the maximum case is negative. Okay, and they're the conditions that would make that true. So this, first of all, is a stationary point. This tells it's minimum. This tells it's maximum. But in terms, if we were asked to describe the curvature or the concavity of this particular stationary point, what's happening is that we're going concave up. It's starting to curve upwards. Okay, so this is called concave up. And here, this is concave down. Okay, curvature, it's now curving downwards. Now, this is really useful because it helps us to identify the third type of stationary point, which is the point of inflection, which is what we're going to look at today. So, inflection point, or point of inflection. And at a point of inflection, the second derivative is actually equal to 0. And we've had the other two options. We've had the positive, we've had the negative. We haven't actually had the equal to 0. This is what it is, okay? And what it means is that an inflection point resembles an S shape, either this or the mirror image of it, okay? An increasing function or a decreasing function. The point of inflection is right in the middle. I'm going to call it POI, point of inflection. And in this case, you can see that this is concave up to concave down. And here we've got concave down to concave up. Okay, so the key thing to know is that once we identify where the point of inflection is, we can then go and analyse either side of that point of inflection, again using the second derivative, to decide whether we're looking at concave up parts of the function or concave down. And if we identify that there's been a change in concavity along the way around that point of inflection, okay, then we can come to the conclusion that it is a point of inflection that we're dealing with, okay? So we sort of justify our answer finding it through the second derivative. We're going to look at an example now and put that into practice. So first example is this. Okay, so we're going to sketch. Okay, the function is y equals x cubed minus 3x squared minus 24x plus 1. Okay, and the conditions are, okay, include stationary points, or turning points, sometimes called. Yeah, stationary points, points of inflection, and axes, y-axis intercept. Okay, so I want as much information as possible that I can get from this without using a calculator. Now, the first thing is stationary points. So dy by dx is equal to, in this case, 3x squared minus 6x minus 24. And I know when it comes to stationary points that dy by dx is equal to 0 for stationary points. Okay, so I'm going to set that equal to 0. I'm then going to divide through by 3. So x squared minus 2x minus 8 equals 0. Let's see if it factorizes to find my x coordinates. I think it's going to be minus 4 and plus 2. So I've got two x coordinates. They're 4 and -2. Now, my next thing that I'm thinking, I'm going to go in and decide on the nature of the stationary points. I'm going to go and find that out using the second derivative. Here's the first derivative. So the second derivative, d squared y by dx squared, is going to be 6x minus 6. And now if I put those values in, the 4 and the -2, into this, I'm going to find whether or not the value of the second derivative is positive or negative. So first of all, x equals 4. D squared y by dx squared is 6 times 4 minus 6, which is equal to 18, definitely positive, therefore that's a minimum. And if I put -2 in, d squared y by dx squared, 6 times -2 minus 6 is -18, which is negative, so therefore that's a maximum point. Okay, so I've got that information there now. Okay, I've got that, and if I started to do my sketch, here's my 4 here, here's my -2. I know I've got a minimum point happening somewhere here, and a maximum point happening somewhere there. I've just got to decide what's happening elsewhere. My next job is to find points of inflection. Okay, now I've already found the second derivative, and I know that at a point of inflection that's equal to 0. So I'm going to go over the page now and write that again. D squared y by dx squared, I found it to be 6x minus 6. Now for a point of inflection, okay, and that's POI, POI, that is going to be equal to 0. Set it equal to 0. So 6x equals 6, x equals 1. So my point of inflection is x equals 1. Okay. Now I need to justify for myself. I need to really assure myself that is a point of inflection. So I'm going to look either side of that x equals 1. Here's 1. What's on the left of 1? 0. What's on the right hand side of 1? It's 2 on the x-axis. I know that the second derivative here is equal to 0. Let's go and check the concavity on either side of the inflection point, and this will tell us whether or not we were dealing with concave up or concave down either side. And if there's a change in concavity, like we mentioned earlier, that's telling us that it is indeed an inflection point. Okay, it only happens, it's only going to be an inflection point if there is that change of concavity. And sometimes you're asked to give extra evidence for that. Okay, so you'd have to use this method here. So first of all, x equals 0. Okay, x equals 0 going into d squared y by dx squared. Well, that's going to be 6 times 0 minus 6, which is -6, telling me it's concave down here. Here I've got the point of inflection. This should be concave up, all going well. Let's have a look. X equals 2. So we put it into the second derivative, and it's going to be 6 times 2 minus 6, which is equal to positive 6. Yep. So that's going to be concave up. So if we actually sketch what's going on here, okay, I'm going concave down to concave up. That's going to be the same as this one. Oh, no, sorry, this one. Concave down to concave up. It's going to be that back to front S. Okay, it's going to be like that. Okay, here's my point of inflection. So now there's just one more thing to do. Okay, I know that I've got something like that happening in the middle. Okay, I'm going to, 1 actually, not in the middle. And the x-axis intercept. Sorry, no, the y-axis intercept. Now the y-axis intercept happens where x equals 0. It's very easy to see. If x equals 0 here, and here, and here, these three terms are all going to turn into 0. It is just the number on the end. It's going to be 1, isn't it? Okay, so the y-axis intercept is going to be at 1. I'm going to start to sketch this now. I've got enough information. So I've got my x, I've got my y, I've got, okay, let's remind myself, I've got stationary points happening at 4 and -2. Okay, an inflection point at 1, there's 4, there's -2, I've got a y-axis intercept at 1, okay, and basically what I found was that I've got a minimum point at 4, Okay, I've got a maximum point at -2, and I've got an S shape, so it's going to have to be something like this, isn't it? And I think I might have to have another go at that. Okay, I'm going to sketch it. So it's going to be a maximum point here, a minimum point somewhere here. I think I'm going to have this down here because we've got this big S shape happening. And then it's going to be heading down here. And yeah, okay, an S shape sort of like that. Okay, all right. Again, it's not the easiest, this. Okay, yeah, okay, yeah, I think it's going to be something like that. Okay, yeah, so we got there. Tricky. Yep, let's make sure we've got everything in. We've got a maximum point, we've got a y-intercept, we've got a point of inflection happening here, and then we've got a minimum point down there. I got there in the end.